Imagine navigating a map by drawing an expanding square from your starting position. The algorithm, known as breadth-first search, explores an unweighted grid exactly like this, expanding uniformly outward in all directions. By treating every grid square identically, it guarantees the shortest possible route, simply counting the fewest physical hops to reach the destination. But geography rarely behaves like a perfect grid. A direct path might cross a massive mountain range, and a straight highway can be paralyzed by a severe accident. When an algorithm calculates a route based purely on physical distance, it completely ignores the friction of the terrain. Counting physical steps actively forces data and vehicles into catastrophic bottlenecks. Take this heavy delivery truck. According to the map, it has a direct one-hop route to its final destination. The problem is that this single geometric step runs straight through downtown at rush hour, trapping the driver in 60 minutes of unmoving gridlock. Alternatively, a winding 4-hop route through the suburbs bypasses the highway completely and takes just 15 minutes. Breadth-first search will always send the truck straight into the 60-minute traffic jam. It strictly counts the number of turns, and mathematically, one turn is fewer than 4. To solve this, we replace physical distance with a weighted graph. Every road segment is assigned a numerical penalty based on travel time, fuel cost, or latency. This map shows the Arizona region, with a dense, intersecting web of red routes and numerical markers. Tracking these kinds of varying penalties across an entire network has historically been a massive routing challenge. To successfully navigate an uneven, weighted world, we have to abandon the uniform ripple expansion and adopt a system that aggressively hunts for the cheapest overall cost. In 1956, computer scientist Dijkstra built the definitive mathematical framework for this by applying a strictly greedy logic to pathfinding. Instead of expanding evenly in all directions, Dijkstra's algorithm utilizes a unique data structure called a priority queue, structured here as a min heap. It dynamically sorts values so the lowest number sits at the absolute peak. This queue asks the system one relentless question. Out of everywhere we have explored, what is the absolute cheapest move we can make right now? If one path costs 5 milliseconds and another costs 50, the algorithm instantly grabs the 5 millisecond option and ignores the heavy route. This diagram of Dijkstra's algorithm shows exactly how that works. The highlighted green edge extending from the yellow node represents the algorithm actively weaving around traffic, locking in a cheap, precise vector. By making a localized, greedy choice at every single intersection, the algorithm guarantees an optimal route to the destination, without wasting computational energy on expensive dead ends. The algorithm's efficiency is defined by its big O notation, specifically E log V. Here, E represents the number of edges, or roads, and V represents the vertices, or intersections. To maintain this speed as the map grows, the algorithm must adapt instantly. If it discovers a faster shortcut to a location it already knows about, it must rapidly update that specific node's value so it bubbles up the queue. Computer science outlines a specific mathematical function to execute this update, the decrease key operation. Without this capability, the algorithm would have to manually search the entire queue just to update a single number. That degrades the processing speed from a sprint to a grueling crawl. Keeping the algorithm within this optimal time complexity is what allows a GPS to calculate routes across millions of possible turns in under a second. But when software engineers attempt to build this in C++, they find that the language's standard template library lacks a decrease key function entirely. The standard priority queue is rigidly designed. You can add items or remove them from the top, but you cannot reach inside and modify a value once it has been inserted. Lacking this tool, engineers are forced to choose between manually searching the queue or destroying and rebuilding the entire structure from scratch every time a shortcut is found. At the scale of modern internet routing, forcing a processor to rebuild these memory structures thousands of times a second creates a massive computational overhead, stalling the packets the algorithm is trying to move. The efficiency of a mathematical theory is ultimately limited by the flexibility of the programming language used to compile it into actual code. Software engineers bypass this missing function by doing something completely counterintuitive: intentional duplication. Instead of searching the queue for the old, expensive path to update it, they simply inject the new, cheaper path directly into the queue alongside it. The cheaper node easily beats the old one to the top, but this populates the bottom levels of the queue with heavy, outdated garbage data that will inevitably bubble up to be processed. That is where a critical line of code neutralizes the threat, the lazy deletion check. This simple logic check intercepts the outdated path, realizes a faster route to that destination was already processed, and throws the data in the trash instantly. This singular, lazy workaround bridges the gap between pure mathematical theory and the rigid constraints of software engineering, quietly maintaining the speed of global logistics every single day.